Welcome to Chemistry at Hononegah High School. Today we'll be reviewing how you determine what the shape of a molecule is. Now, the guiding principle behind finding the shapes of molecules is what's known as Vesper Theory, valence shell electron pair repulsion theory. Now, since that's a mouthful, we usually refer to it, as I said, as Vesper Theory. And the actual acronym, if you look at what the words are, it pretty much tells you exactly what it stands for. So valence shell electron pair, well, your electron pairs on the outside of an atom, your valence shells, which are what we're drawing when we do our Lewis dot structures, repel each other because they're negative regions of space, basically. They're electrons. So they're going to orientate as far apart as possible. So the actual words within the acronym tell you exactly what it stands for. Now, written out, it would be electrostatic repulsions. That means, opposite charge, like charge situation, so positive and negative. Like things like electrons, negatively charged, are going to repel each other. So repulsions between valence electron pairs surrounding an atom cause these pairs to be oriented as far apart as possible. So basically, we're going to always spread out our electron pairs. And that's going to determine what our shape looks like in 3 dimensions. And one of the difficulties with this is we're looking in 2 dimensions when I draw something for notes here or write it on a board or you look at a picture, you're seeing in 2 dimensions what actually exists in 3 dimensions. And that makes that a little bit more difficult for some people than others. So if you're good at visualization and you understand spatially things around you, like you can often tell which direction north is as you've moved around wherever, you're probably pretty good spatially, and that may make this a little bit easier for you than others. Now, if you have difficulty, I set up kind of a cheat code you can use to help you figure out the shape until you get better at it. Now, the first shape we're going to look at is the one that's easiest. 2 atom molecules are always linear. So it doesn't matter how we orient it, how we spin it, what we've got. If we have 2 atoms, 100% of the time that's going to be linear because in math class, 2 points define a line. So 2 atom molecules, any binary, or I should say diatomic situation, 2 atom situation, or a binary molecule where you only have one of each atom of each element, they're always going to be linear every single time. So that one you don't worry about anything. It's automatically linear. Now, when we have more than 2 atoms, it gets a little bit more complicated, but not much. And one of the things we're going to do is we're going to break things into our symmetrical versus our non-symmetrical shapes. So you can start seeing the concept of symmetry we're going to use in our next set of notes. And I'm also going to give you a code that you can use to translate the molecule to see exactly where it fits on this diagram. So if we have 2 atoms on the outside, one of 2 things is going to happen. It's either going to be a situation where they're all in a line, or they're going to be an angle between the 2. So for 2 atom molecules, we have either linear or bent. So it's either going to be a line or it's going to be at an angle between our atoms. So A stands for, so here's where the code comes in. And remember, on the test, there's nothing about A's, B's, and E's. This is just something you can use as a tool or a crutch to help you see shapes if you have difficulty with it. A would stand for how many central atoms you have. They're all going to have one central atom. We're dealing with simple molecules. So there'll always be one A. Really, the key is B's and E's. Now, B is how many outside atoms you have. So in the pictures I drew up here, this would be my A, so what is in the middle, and my B's would be what I've got on the outside. So in both these situations, I've got 2 atoms on the outside. That's why I refer to these as AB2 situations. So you'll notice in the type of molecule, looking at the type of molecule column here, this is really what I call my cheat code. So after this, I'm not going to talk about it as a type of molecule. I'm just going to say, what's the cheat code say? Well, every one of these cheat codes is an AB2. Now, what's different is some of them have an E as well. Now, what E stands for is unshared electron pairs on the center atom. So if you actually look at your electron dot drawing, for something like water, water is H2O. So when I draw H2O, it's going to end up like this. And I'm going to have 2 electron pairs on that central oxygen. So this would be what I call 1 in the middle, so an A, 2 in the outside, so B2, and it has 2 unshared pairs. So this is AB2E2 when you look at the picture. So if you look at water and you don't see it as bent, you can write its cheat code and you can see, oh, water has to be a bent shape. So when you look at the code, you can always figure out what shape it's going to be. Now, the concept of symmetrical is really tug-of-war symmetry, because when you look at water, it may look kind of symmetrical to you. But in 3D space, what we're looking at is if we had a tug-of-war. If I have two atoms exactly opposite of each other, 180 degrees between, and they're pulling exactly opposite, they're going to end up canceling each other out, and that's what I mean by symmetry. In our water molecule, they're not exactly opposite. Our electrons are moving in that direction, so they're both moving up, and there's nothing in the upward direction to push down at them to cancel it. So these are not directly opposite. So what I'm really talking about with symmetry here is tug-of-war symmetry. If we had two people pulling exactly opposite with the same force, they cancel each other, just like that happens basically in this situation here. But if I got something like water, which is bent like this one, they're not really exactly opposite, so they're not going to cancel. So that's what I mean by our symmetrical shape. Now, the key to notice here, and this is something that I'm just going to point out, but we're going to come back to it, is the difference between symmetry and non-symmetry is going to have something to do with that A. So let's continue on and look at some of our shapes and come back to that idea. So that would be if I have two atoms on the outside, it's either linear or it's bent. Now, if I have three atoms on the outside, we're talking about a triangle situation. There's two types of triangles. There's a flat triangle, and then there's a triangle that's in a pyramid. So we call it trigonal planar or trigonal pyramidal. So are they truly exactly opposite each other and flat like that? Or are they really more like this? So it makes kind of a pyramid if you see it. So there's two types of three on the outside, or AB3 situations. And that's, once again, the difference is, do we have an unshared pair? If I have an unshared pair, then I'm going to end up with this situation, which is my triangle pyramid. So remember, this kind of looks like a pyramid here. If I don't have an unshared pair, what I'm going to end up with is my triangular flat situation, or trigonal planar. So once again, the key is, do I have an E? So notice, in every situation where I had an E, I got the non-symmetrical form. In this case, this is going to be the pyramid versus the planar. So in our planar situation, if I have three people pulling exactly opposite each other in a flat plane, they will perfectly cancel each other out. But in this top situation, if they're pulling and they're all pulling down, and there's notice nothing up here, there's no atom up there to pull in the opposite direction, they're not going to be perfectly canceled by each other. So if they were all pulling down, our pyramid, so to speak, would be moving downward. So that's our non-symmetrical pyramidal type situation. And the difference between the two is whether you've got that E there. So as you do these, if you're good spatially and you start to see it, you don't need the ABE situation. But if you're not quite sure what it is, use the A, B's, and E's. It will always tell you the right answer, as long as you know how to write the A, B, E, and your electron dot is correct. Now, 4 on the outside is our symmetrical tetrahedral shape. So in this case, it would be like the trigonal pyramidal, where I have 3, but now I've got 1 going straight up as well. So what I get is a 4-sided figure, which is a tetrahedron. So we call that a tetrahedral shape. Now, there's no unshared pairs in the center atom. So this would be something like CH4, which has got a carbon, and then it has 4 hydrogens coming off of it. There's no unshared pairs there. So that would be AB4. That would be our tetrahedral shape. Now, the last two shapes are our expanded octet shapes, because remember, we can sometimes have things with more than 4 bonds. So technically, that doesn't follow the octet rule, but they do still exist. So if we have an AB5, 1 in the middle and 5 on the outside, like PCl5, then that would be an AB5 situation. And what you've got is a trigonal bipyramidal, because what really happens is if you have 5 things, so in the case of trigonal bipyramidal, so let's look at something like PCl5. So I've got 1, 2, 3, 4, 5. What I basically have here is 2 pyramids exactly opposite each other. So I've got this pyramid there, and like I've got this pyramid here. So what I really have are 2 pyramids opposite each other. Bi means 2. So they're both triangle-based pyramids, and they're perfectly, one going up and one going down, so to speak. So what I get are 2 pyramids. So that's why it's bipyramidal. And if I have 6 on the outside, what I actually get is an octahedral shape. If you actually have one in the middle, and then 1, 2, 3, 4, 5, 6 atoms coming off of it. Now, you're looking at a two-dimensional representation here, so it's really hard to see this without seeing it in real 3D space. You would actually have an 8-sided figure, and we call that octahedral. And both of these shapes, the trigonal, bipyramidal, and the octahedral, they're perfect symmetry types, or they're symmetrical type situations. You end up with 5 or 6 things really exactly opposite, canceling each other out. Now, the one thing about the expanded octet too, the trigonal, bipyramidal, and the octahedral, while you're going to see these in homework, and we're actually going to see some of them in the model building lab that we do, this is beyond what we want you to memorize for the test and be able to do. So remember, don't worry about knowing these for the test. In the homework, when you see one, you can always look it up in your notes here to see what the shape is going to be. But on the test, you'll never be asked the shape of this thing. You might be asked, does this follow the octet rule? And you'd look at it and say, oh, it's got 5 things stuck to the middle or 6 things stuck in the middle. No, it can't follow the octet rule. But you're not going to be asked to memorize those shapes. So you don't need to worry about them. So when you draw your electron dot, write down your ABE code, and you can see which type of shape it is. And hopefully that helps you understand the different shapes that you need to know.